Hello. I mean, this is our first proceedings. No. Hey, yes. Oh. Never felt so powerful. So yeah, this is our first proceedings. So for those of you who don't know me, I'm Toby, and so I'm a member of the PhilSoc committee, but also doing a PhD in physics here. I'm one of the few physicists who actually likes philosophy. So over the next kind of 45 minutes or so, I haven't timed it, we're going to be looking at kind of ancient Greek ideas of space-time and kind of Newtonian Enlightenment ideas of space-time. And we're kind of doing a modern retelling, so we're going to be using the maths introduced by, don't worry, there won't actually be much maths in it, but using the ideas inspired by the maths of Einstein and Minkowski and things to kind of backtrack and look at these space-times kind of through this modern lens. And as much as it's kind of historical, the history is by the side in terms of, and giving way to what I hope is a nice and understandable narrative. So, I mean, it might be odd that we're looking at these kind of disproven theories, but actually out of these theories, we can see many of the ideas that are still relevant in modern physics, the ideas of kind of dynamics, cosmology, symmetry, space-time, and how they all still relate to each other. And it still brings up many of the same philosophical questions, things like scientific realism and how to decide, and if you have a range of equivalent entities, which one is real, is it all of them, kind of what's the ontology there? And because it's a proceedings and not a lecture, and I know James is very excited about this bit, it does mean you're allowed to ask questions and heckle at any point. And because it's meant to spark discussion as opposed to me just presenting an argument, I have got a range of questions, and this is the only slide. I'd made it in the pub earlier. So kind of on the more philosophical end, there's the questions of, if we emptied out space-time and time of all objects, so all there existed is empty space, would it still exist? Or is it only the relationships that exist? And as I just said, and the other question is, in many of the cases, there's a range of equivalent space-time structures or choices to make. And in which case, which is true, which exists, how can you even decide that question? Then kind of on the physics end, are any of the space-time structures I say actually experimentally different? Or is it just that the definitions I use of force, motion, space and time so intertwined that actually everything's circular? And for anyone who has done kind of a higher level of maths, I will give the mathematical structures of these space-times, and there may or may not be structure I've missed or pre-assumed. So what have I missed in writing down the kind of more mathematical side? But don't worry, there's literally 4 equations and they're completely irrelevant to the story. I just couldn't help myself putting them in. So one is, what does it even mean to have a theory of space-time? And I mean, I think an easier concept that will come up in everything is that of a force. And I'm going to define a force purely operationally. And that is, a force is what causes an elastic band to stretch. And I won't go any further because it's kind of related to the middle question. And for those of you with a physics background, I'll introduce a few kind of laws of motion, equivalent to Newton's second law. And there's some interesting ideas, Leonard Susskind discusses them, about how these laws of motion, particularly when it comes to just simple harmonic motion, kind of there's interesting ideas about kind of information conservation there, but I won't really touch on that. And I'll just define space-time to be the background in which everything happens. And everything that happens at a point in space and a point in time. And our theory of space-time is just the relationships between these points. So the first space-time picture, kind of the traditional one, the kind of intuitive one you'd all have, is kind of one that comes across, well, it's, again, I'm being fast and loose with history, but it's the Aristotelian space-time. And if we make 2 assumptions about the world that comes from Aristotle's physics. So, firstly, the Earth is at the center of the universe, and there's we call them celestial spheres around it. But what's important is the Earth is at the centre, then there's kind of different layers of the planets, and then the stars in the background. An alternative, and on the dynamical side, so that's the kind of cosmological assumption about the world. He also had a dynamical assumption, or a dynamical law, which is objects are naturally at rest somewhere. So if we look at just everyday objects, they have a natural place to be, which is at rest on the ground. And then he also had a law of motion, equivalent to Newton's second law, which is the harder you push, the faster things move. So, and again, that's what I said about Susskind. There's potentially interesting problems of conservation of information there. But, so what can we deduce from these laws? So in fact, I'll draw a little picture of what he said the universe looked like. So he had the Earth in the centre. Yeah, these are arrays markers, that would be awful otherwise. And then spheres of planets around. And secondly, he had the law of motion, force is just proportional to velocity. Don't worry, there won't be too much maths, I promise. So what can we deduce from this? Firstly, that there is a centre of the universe. There is a special point, a privileged point, right, where the Earth is. And from this privileged point, it makes sense to meaningfully say where you are in the universe as a whole. And the fact that objects are naturally at rest, and that force causes motion, you can meaningfully say how fast and in what direction you're going. And these may seem like things you can do anyway, right? This shouldn't be a shock, this space-time picture. This is the one you all would have grown up with before you were told the Earth is round and moving. So the kind of picture that comes out of this, and I can't draw in 4 dimensions, so I do apologise, but the kind of picture that comes out of this is a space-time where you have, so this flat surface is space, and it extends through time. And I'm going to place the little axis for time in the middle. So this here is time. And I apologise for my handwriting. It's not going to get better. Teachers have told me off for 15 years. So in this picture, we have 3D space and we have a time. And I fixed the time direction to the centre. So there is a fixed centre. And this flat piece is 3D space. So there's a fixed space and a fixed time. And this allows you to say individual points. So this point and this point, they're meaningfully different. They're meaningfully in different places. But this leads to something. If this point is fundamentally different from this point, why should the physics be the same in both of them? And in fact, if there's no reason for the physics to be the same at any 2 points, why should they be? And in fact, we'd kind of expect them to not be. I mean, equivalently, if you would take the entire universe, you pick it up, you magically and instantly transported it somewhere else, you'd know. The physics would be different. You'd be in a physically different point. And you would be able to tell this by the different laws of physics. And this is the connection with symmetry, which we'll see again and again. There is no symmetry between picking up the universe and moving it. And we'll see this may seem kind of trivial now, but we'll get back to it again and again. And because there's no symmetry in our space-time structure either. Now, but what if we changed our cosmology? So we still keep the law of motion, but this time we assume there's no centre of the universe. You know, we've heard of Copernicus and Kepler, and we know that planets are just planets. And we know we're not special, and the sun moves around and there's other stars. In this case, there would be no longer a centre. And this means there's no privileged position, and all points are therefore equivalent. If you were to pick up the universe and shift it and put it down somewhere else, there's no way of knowing. If you do it to the whole universe at once, the laws of physics are the same everywhere. There's absolutely no way you'd know. So, back to the symmetry, this means the universe is symmetrical under these magical and instantaneous transformations, these transportations. And we want our new space-time, so the kind of the upgraded version of this, to reflect this transportation symmetry. Yes?
Sorry, so why does heliocentrisity imply in translational symmetry? When you have a fixed sun, for example, why is this different from having a fixed Earth? Do you understand what I mean?
Yeah. So the question was, well, okay, we've put the sun at the centre of the universe. That still gives us a fixed point. And yes, if you go from there, it would be. But again, I'm kind of being a bit loose with history. I'm assuming that we've kind of accepted the sun as just a star. I mean, I've heard the space-time called the atomist space-time in Joe Keir's lecture notes, but I haven't found a source for why he calls it that. So I'm just relaxing the cosmology to see what comes out of it. However, even though we've relaxed the cosmology and we therefore have equivalent points now, we still have this. Force is proportional to velocity. So we can still say, objectively, how fast and in what direction something's moving. That is, if we were to magically and instantaneously speed up the universe, we'd know. Just as if we knew here by the changing of the laws of physics, if we sped up the universe, we'd feel something. We'd feel a force pushing back on us or something. I mean, there's an alternative way of saying this. So this means, here there's fixed points, but if you have fixed velocity, even though you can't say, I am here, you can still say the point now, this position now, and this position in 6 months' time, 1 million years' time, tomorrow, is exactly the same point. That's still a meaningful thing to say. So the space-time picture that comes out of this may be hard to see why it's different from that, just by the drawing. But what you have is you still have, space kind of looks the same. It's still, well, in our case 2D, but in real life 3D. The only real difference in the kind of picture that you'd have in your head is now time isn't attached anywhere. Right? There's no fixed point to attach time to. Does this make sense? Yes?
Does that mean that in the first view, time was attached to the central of the universe?
It's more of a picture. So when you draw like axes, like on a, there's sometimes there's like a zero in the middle, and that's the origin, and that feels special. So that's what I've done here. I've put time through the center, but here I could attach time equally well to any point, or in this picture, not really attach it to any point. It's hard to draw 4 dimensions on 2D, but is this picture slowly making sense? I'll take that stunned silence as yes. Okay, so that's the ancient world, and they were wrong. So, who booed? So if we then move forwards into kind of what was now being known as Galilean space-time, but kind of, as far as I'm aware, that was kind of, this name was given to it by Weil in the start of the 20th century. So we still have the cosmology still the same. We go back to Newton and Galileo's day, we still accept there's no centre of the universe. That's still fine. So that means there's still no privileged centre, there's still, points are still equivalent, and there's no good way to define what it means to be here. All I can say is, I'm next to the computer. And Newton came up with a different law of motion. And this is the one you would have seen at school, or I'll run over here. Wasn't expecting the lecture to be so tiring. So Newton's law of motion, most of you will have seen this, is just F equals ma. And so this means that velocity as well is no longer kind of built into the theory. How do I say this? And he also obviously had his first law. So if something is at rest, it remains at rest. And if it's moving in a straight line, it continues moving in a straight line. And so, and this here, unlike saying F equals mv, which says velocity is well defined. We now only say acceleration is well defined. So we no longer even have the idea of absolute motion. So if the universe were instantaneously and magically sped up, we wouldn't know. Aristotle says we'd feel a force. Galileo and Newton, if we just sped up to a fixed speed, we wouldn't know. So now, not only can we not say where we are, we also can't say how fast we're moving. Yes?
By sped up, do you mean that time speeds up, or do you mean by like actual everyone's motion?
I mean, if this is everyone in the world,
Yeah.
and it's staying still, and then I make it move.
Okay, cool.
Yeah, I don't mean time speeds up. And because there's no way of saying who's still and who's moving, there's no way of actually saying if the same point at different times are the same point or not. Yes?
Second question on the same issue. If you're saying we're speeding up, do you assume that the space-time itself is accelerating or moving, or is it just the opposite within space-time frame?
All I've said, well, that's kind of related to the questions there. Is it moving space-time? Is it moving us? But you wouldn't know. This is the thing. It doesn't necessarily even make sense to say. If you take the entire universe and make it move, how would you know? What does it mean to say that? That's the point. So, this sense, the fact that you can't say this point is the same point, so the point I originally started the sentence at and the point I'm saying it now, there's no way to even ask, are they the same position in space? All I can say is I'm at the same place next to the computer, next to the front row, and so on. So the picture that comes out of this, I need to run back and get a pen, is maybe a bit of a shock. So, we still have time here. And now, rather than having space as one big block, space is actually more like a set of shelves. Each space here is a different copy of 3D space. Mathematically, for those who have done physics, you could call this a fiber bundle. I wanted to get that in. And so each copy of space here, you can't really say that this point on this bit of space is the same as this point on this bit of space. They're separate. You can't really say this. But have we lost all structure here? Have we just kind of gone away with everything that we consider intuitive and nothing is real? Well, I mean, we still have time, right? In all of these theories, time is still the same. I mean, there's a great quote from Newton, which is, "Absolute true and mathematical time, from its own nature, passes equably without relation to anything external." So time is fixed, it flows. No one really changed what we thought about time until Einstein came along. But from F equals ma, so by saying that force is related to acceleration, we can still say if something is speeding up. So, if we plot, I'll get more colours. So glad I bought these. So, if we have an object moving through space, let's say there's no forces on it, that's going to be a straight line. However, we can't say how fast it's going. So we can't say if it's a direct straight line or a straight line at different angles. We have no way of knowing which of these it is. And we can slide these shelves around in any way as long as straight lines remain straight. However, if you have an object that's speeding up, it will be a curved line. So we can do anything as long as we don't make these straight lines curved. Yes?
Those straight lines are space.
So the flat black lines are space. The red lines are an object moving through space.
Moving through space, but not moving through time, or could be both?
Moving through both.
Moving through both.
Moving through
Then
both.
Why is it curved if it's speeding up? Is it slowly speeding up, so that's why it's Or is that just back the road?
So the steepness,
Yeah.
so if we imagine now that, okay, so the steepness of the line is how fast it's moving.
Okay.
However, that's only relative, right? I can only say that this is moving faster than this,
Yeah.
or this is moving faster than this, because I can slide all the shelves around and I can make this one straight up and this one point to the left.
Yeah.
However, what I can't do is shift the shelves around so that this one becomes straight.
Okay, got it.
Okay. And how much it's curving is to do with how much it's speeding up. Although the steepness, the current gradient, is the speed. And this is kind of where A-level mechanics would have left off. And the next sort of paradigm shift comes from Einstein, and, well, we only have half an hour left, so we're not going to get there. However, it wasn't as clear-cut. So I've given you kind of 3 pictures of space-time with a nice historical picture, I hope. It wasn't as clear-cut back in the day. So Newton and Leibniz disagreed on basically everything. They disagreed about this as well. So Newton actually believed in absolute space, which is this picture. So he believed that it does make sense to say if something's stationary or it's moving. And he got this from what's been known as the bucket argument. If you take a bucket of water and you spin it, what you'll see is water go from the middle to the sides. However, there's no relative motion here. The bucket stays the same, like the parts of the bucket are all the same point relative to each other. There must be something real about the spinning of the bucket that causes the water to be pushed out from the center. However, still by Newton's laws, and he admits this, is that even if he believes the bucket argument said there was absolute motion, there's still no way to pick out who's in absolute motion. So he's put it in this structure, but there's no way to test for it or find it. Leibniz had a problem with this. So how do you find that if there's all these different, indiscernible space-times, how did the universe choose which one to be? And if there's this free parameter of what is the natural resting speed of the universe, and it doesn't matter what that natural resting speed is, how do you work out, how do you measure that? How did the universe pick how fast to be going? And he didn't like that. And so he believed there was only relative motion exists. It only makes sense to talk about, doesn't make sense to say how fast these 2 pens are going, but only how they're moving relative to each other. But that doesn't explain the bucket argument. Or really, several other things from Newtonian mechanics. And there are ways out of this. So you can argue, one, from kind of an idealist point of view, that, well, if you're imagining a spinning bucket, you exist. Like, you have to imagine the spinning bucket. We don't have intuition for an entirely empty universe with nothing but a spinning bucket. So you can't even do the thought experiment. Alternatively, there are ways of picking a universal rest frame. So there's Mach's kind of theory of mechanics, where he uses the distant stars we see, and he kind of works out what their average velocity is, and that's a special frame in some ways. It feels like, I haven't found this in physics class, I've spent a lot of time looking up where to find these models. But there are ways of picking a universal rest, but that is entirely relational, but it feels to me at least a bit forced. And there are other models which, again, so rather than having positions, so rather than having an equation of motion that tells you about positions of particles, you have equations that relate the shapes made out by the different objects. So if these three pens make a triangle, you can say not how the individual points move, but kind of how the size and angles of this triangle move as a whole. Again, but these models are ridiculously mathematical, and I haven't spent time going through the maths. And so in many ways, the Galilean space-time is the kind of compromise between these two views. It gives the minimal requirements for Newtonian mechanics, really. And maybe this kind of detour may have been tacked on to the end a little bit, but there is a really interesting question that comes up every time there's a symmetry in physics. And as a particle physicist, this comes up daily. Whenever there is a symmetry, so in our case here, how you slide the shelves. In this case here, well, which point do you stick time to? Are all these equivalent systems, are they physically different? Did the universe just pick one? And in which case, how did it pick it? Which one did it pick? How would we know? Or is it actually the kind of set of all possibilities that's real? And this comes up every time there's a symmetry. So in particle physics, I mean, all of particle physics is a gauge theory, which is symmetry. So it's potentially a question that comes up to a lot of physicists. And to be honest, this is actually everything I'd prepared. So, and I don't have an argument to conclude with, because it's physics, we don't do that. And so actually, and because this is a proceedings, I'm going to draw your attention back to the questions and just open the floor for discussion amongst yourselves, or for heckles, or for any criticisms at all. Thank you.
So, when you're talking about the absolute resting speed of the universe, do you mean what would consider a straight line in this graphic, for example?
Yes, so what I mean is, so in this graphic, I said there's no way to say which line is directly up versus curved, right? You can slide the shelves such that that's true, such that you can go bucket, the water spills over the edge. And that needs explanation. And Newton does explain that. And Galileo explains that by picking out a set ways you can organize the shelves. But without modification, Leibniz doesn't. Yes.
Could you explain a bit more about why relative position like what's not the spinning like the fact that it's not explained by them?
Okay. So let's have the bucket here. So let's say the bucket's got a handle. There's two handles. What else is on a bucket? I don't know. There's a hole here. Now let's spin the bucket. Oh, wait, the bucket's still the same. All I know is this distance, and this distance. If I spin the bucket, none of those distances change. So if all that exists is the bucket, how does it know it's spinning? If all we have are the distances between things. So without having something it's spinning, a space it's spinning relative to, how do we say the bucket's spinning objectively? How do we explain the fact that the water spills? Yes?
Going on that same line, how does the picture of relations between frames and the fictitious forces play not only into the bucket but the whole picture cosmology played out in real life?
Do you mean, what do you mean, as in non-inertial frames?
In general, yeah.
So, yes, you can be, so you can exist in this, like you can put your foot down on an accelerator and be on this line. And to you, it would look like these are bent. And the way to rectify that with Newton's laws, so if you're on this curve here, and you see these lines bend, well, you have two explanations. Either one, you're moving, and you are, right? There's a force on you. We can say you're speeding up. Or you have to say that there are extra forces acting on these lines, and it's that which you'll call fictitious forces. They come from assuming that even though you're on a curved path, you're actually on a straight path. So that's how they fit into it. Does that make sense? That's potentially more of a mathematical idea. Yes?
You make a curved line straight by shifting the shelves.
You can, but Galileo says that's not allowed.
Okay, got it.
So that's the point. Yeah, as much as it's possible,
Yeah.
it's not allowed. This is what he was saying about fictitious forces. If you do that, then you'd have, in order to make that fit with Newton, you'd have to invent forces for this. Are there any more? Yes. Pardon?
So, could you not suggest that the points on the bucket are feeling force as they're spinning around?
Who did Newton?
No, I'm asking like, did the idea of non-inertial frames exist before?
I mean, like Galileo had the idea about inertial frames, and the first law comes from there. So it does. This is why this is called Galilean spacetime, even though, as I said, it was invented, I think, by Hermann Weyl in the early 20th century.
Why would Leibniz be able to explain the environment of the bucket? You could say that the points are non-inertial.
Well, because if you only have relational things, how do you define inertial? You have to pick to define inertial frames on here, I already have to tell you this line is straight. Then you can say if every line is straight relative to it. If I were to move all of these so this looked straight, then this would look inertial on the picture, but you have to basically be given that information ahead of time. Once you have one inertial frame, you have all the others. But if all you have is relative motion, you don't have the set of inertial frames already.
Because we know at a certain point fields are force or not. Right? Isn't this how we define inertia or non-inertia? Whether the body is feeling force is experiencing force.
So
So wouldn't we be able, what I'm saying is like, wouldn't we be able to define non-inertia or inertia objectively?
Yes, but then that assumes a lot of knowledge about the way forces are between different frames. And yes, in all of this, forces are objective. I mean, Leibniz didn't really have a whole theory of mechanics based around this. And so lots of the ideas are a lot more modern. So actually, if you ever do general relativity, I think Friedrich Schuller, he has a set of lectures online, and he goes in a lot of detail about what the first law actually is. And the first law, you think it's included in the second law, right? If you have a force, you have acceleration. So if there's a force, there's already you already know if something's inertial or not. But that gets difficult when you have gravity. Gravity is or isn't a force. We're not going to get into general relativity. But alternatively, you can use the first law to draw a straight line. I throw a pen in empty space. I was about to throw it, then I realized that's not going to happen. If you throw a pen in empty space, it follows a straight line. And that tells you which line is straight. So you can view the first law as a test for what you mean by a straight line. So I think if you study general relativity, that becomes more important because straight lines are curved. And the first law, in a way, tells you what's the straightest line you can be in a curved space. But that's definitely beyond a public lecture. Yes?
That's the bucket argument that makes it partially bypassed by applying slower scale. So thinking about molecules instead of the bucket as a whole. Because, well, the water is trying to flow out because of certain the rotationary force. I think. So that one point on a bucket, let's say the left handle or the bottom handle, starts moving, but the water inside the bucket doesn't. So there is actual movement, even if the only object in space-time is the bucket itself.
Well, why does the water stay still? You're right, if I grab a bucket and I spin it, the water starts off not moving and only the outer bucket moves and the water slowly speeds up. But why does the water stay still?
First law of motion, again, if there is no force acting on the water initially, there is no movement.
But that already assumes that it was inertial. And if you don't have this background structure of what is stationary and what isn't, all you have is relative positions, and the bucket instantly started spinning. Well, the water, how would it know, right? What causes the force? This is what I mean, yes, you can get around it by saying, well, I pick up the bucket and I spin it. Or I start spinning it. Or, if I start spinning it with my hands, then, well, I'm staying still. So, me spinning the bucket, that's fine, that gets around it. However, we don't have intuitions, right, for a universe that just has a bucket in it. How do you know when you're spinning the bucket that's any different from you running around the bucket, keeping it still? If you just have a universe that's kind of empty, one response that does save Leibniz is that we just don't know what would happen. There's potentially get-outs in any way you do the experiment of the person who spun the bucket, it's moving relative to the Earth, the planets, the sky, the cosmic microwave background. And Mach did develop a theory based around that. However, it took a long time to do so. It doesn't fit nicely with Newtonian mechanics without a lot of extra equations. Yes?
I think, it might be trying to make sense of something that we know doesn't work, right? Like we know intuitive mechanics don't describe things that actually happen. So we know that any presuppositions of that theory would be totally wrong.
Yes, but it's still the same question arises repeatedly in philosophy of physics, where how do you decide what's real? So, the example in particle physics is very hard to hard to describe without a lot of maths. But I mean, even in Einsteinian space-time, there's still a lot of freedom. In which case, if you have this degree of freedom that you can never measure, did the universe pick a single value, or do all values exist at once, simultaneously, as one big universe? Does this make sense?
It makes sense, but I don't quite get how it relates to the problem.
You were saying, what's the point of looking at outdated theories?
So the question is, how do we pick up an objective referential, right? Basically. How do we know that if everything is relative to everything else, there is no absolute referential?
I mean, some things are absolute, right? We can measure them, but within the maths of a theory, there's often degrees of freedom in the maths, which are necessary to make the maths either doable or easy.
When we pick up degrees of freedom, for example, if you have two geometrical symmetrical plates, how do we know which one is the original one? Is that the question?
Potentially a bit more abstract than that. With space, the example was if you take the entire universe and you shift it slightly, are they physically different universes? One and another one that's 2 feet to the right? Or is it the same universe? Like, does that make sense to do? Are they the same? Is the original universe actually this kind of continuum of choices? And that is the same question that comes up again and again, and it's just kind of nicely illustrated with these pictures.
So the question is, how do you know that the universe isn't being, like, for example, shifted around
Yeah.
everywhere, everything at once?
Yes. And if it's not, well, why did it pick the position it is? Or does it even make sense to ask the question, why isn't the universe being shifted around? Because you can't shift the universe around because it makes no sense.
I think the second one.
Well, I'm being agnostic. Yes.
Are all of these theories so far presupposing a spatially finite universe?
So that is the final question. I haven't actually assumed, I've drawn a line to the box, because I have to draw something. It would be very difficult to draw something that's infinitely big. If space had a boundary, then there would obviously be a center, because you could just average out the points. It's still possible within these pictures to have a space that kind of loops round on itself. It's not against them per se, it's easier to assume flat and infinite, but it actually doesn't matter. Yes.
How do the paths that things take in space and time tell us about the degrees of freedom or the structure of the universe?
They tell us by asking which paths are equivalent. Is everything so much of this comes from symmetry. And the point is, this path, if the universe was sped up and instantaneously changed so that this path became this path, there's no way of knowing. So your underlying maths, underlying picture of space-time, must say that this line is equivalent to this line is equivalent to this line. Because if you had a universe where they are physically equivalent, you can't measure a difference between them, the universe itself, like the maths itself, wouldn't. Or you would like the maths to not say there's a difference between them. Does that make sense? So here, we go back to these, right? This one, we had a centre of the universe. So we want to be able to say that this point and this point and this point are different. Here we didn't. So here, we want the universe. So since every point is the same in the sense that if we pick up the universe and shift it, there's no way of knowing. You want a mathematical structure that kind of has that built in. Like here, you can imagine there's forces or whatever, changes as you go further out from the centre. It's possible, but it would be remarkable if nothing changes as you go out from the centre, considering there is an objective centre to the universe. The fact that nothing changes implies, well, if you can't tell where the centre is, maybe there isn't one. So it's partly like you want to have a minimal structure that explains everything. It's possible, yes, to do everything you can with this space-time with this one and just set all changes to zero. But that feels like you're adding things that you don't need to add and isn't kind of what's done. Yes.
Got a question for the more philosophical and about the space-time. Do we assume, like, can it be said that space-time is only it is a reference from an observer to other points? So even because if you close your eyes, you can say I'm here, even though you don't know where here is exactly. And if there's nothing to relate here to, it doesn't mean that here stops existing. So can it be said that space-time is abstract or is fixed in a way that even if you take any other object in the universe except the observer, it still exists because you still have point 0, 0 here where the observer exists. Because you can obviously get countered by saying, well, let's take out the observer as well. But it's a question of if there's an empty forest, does the falling tree make noise? Like, we can't state that.
So
The relationship is, the question is whether the relationship between observer and an object or two objects.
I'm not entirely sure I understand the question. Which, you're saying on the end, are you talking about the top left question?
Yes, top left.
So in that case, if you only have an observer, and you said, I'm here, you shouted, I'm here, yes, you're where you are, but where is here? What does it mean to be where you are without, unless there's other objects or other people that can hear you shout here or other objects with which you can see or whatever? What does it mean to say you're here? Does that, I mean, the point is, I mean, in the different pictures of space-time, that sentence has different meanings. In this picture here, it has a very obvious meaning, right? You are here, and here makes sense. Here, it makes less sense, but you can still say I'm in the same point I was yesterday. Here, you can say you can't even say that. You can't even say you're in the same point you were yesterday, let alone I'm in an objective point. I mean, part of that question is, if you were to get rid of every point, what is even left of space-time? I mean, the point is Leibniz would say, well, nothing. All that exists are relational points. But kind of the other theories do suppose there is something there that's kind of real in some way. But Leibniz doesn't, and there are ways to make that work. Yeah?
What I was trying to say is, well, if you assume, because in Galilean space-time, you can say that point 0, 0 is in any point in space-time, basically, because it's all good.
Yeah.
So the observer is at point 0, 0. And even though we cannot really state the relation of that point to anything else, if we take everything else out of the universe, the basis of system of space, that is 0 point, still exists. So can one argue that space-time or space cannot be deleted completely, or is not just relationship between things?
So in pure Galilean space, there is still some structure left. saying you're at 0, 0, the point is you can do that anywhere. And even built into the physics, that's just a choice you make in order to do some quick calculations. You can do physics without even introducing. Obviously, when you do physics at school, you have to say you start at point 0 and you finish at point 4. But it's kind of very obvious, even from those equations, that it really doesn't matter. This is very true if you ever do general relativity, where every possible choice of laying down coordinates is equivalent. And there's a lot of problems there that are actually kind of interesting. I mean, I can potentially go a bit more into the maths at some point, but maybe not now.
Might take a bit too long.
Yes. Are there any final questions? Because I think there's a final of some sort in here. I don't know whether it's a music competition or an actual exam or just... Yes.
Are you familiar with the Pythagoras theorem?
Yes, briefly.
So how would you say that this is a current understanding of space-time?
I would say classical theories are... So for those who don't know, there's kind of A and B time, where I may have got this the wrong way around, but A time is essentially only now exists, and B time is the past, present, and future. I want to say exists now. The phrasing I've heard is exists in parity, but the point is they all exist at all times. I would argue that these classical space-times are kind of ambivalent. Because there's a now, it doesn't really make a difference whether or not you have the future exists now or not. And you can do quantum mechanics on these, and in which case, then there's a measurement effect that definitely makes the past and future different. If you go to general relativity and special relativity, there's, as far as I'm aware, no way to make A time work. I mean, they might be, there's not one I've seen. So in that case, in special relativity, you essentially need the past, present, and future to exist at once. Actually, no, there are ways, but they're like bordering on solipsism. And I can send you a reference if you want on how that would work, but yes. So you can, but why would you? I mean, you would in calculations. It's what you do every time you do a calculation, you fix a 0. But if you're trying to construct the most general object, yeah, you can, and we can do everything we can do in Newton's space-time on this. But you've added in loads of extra information and detail and structure that you don't need. So this, even though it looks more complicated, is actually, this top right one is a special case of this one. More than, even though that one looks more detailed, this is a special case. Yeah, you can do that, but why would, apart from making calculations easier, but then it's kind of obvious that you're just doing it for convenience. There's no reason to, you don't want to build your entire picture of the universe based on what makes calculations easier. Yes, and I think this will have to be the final question.
It's a yes or no question.
Okay.
Does this string of one version of space-time, being a special case of the other, keep going and going and going until general relativity, or is there some product?
No, so you can't derive, so like Newtonian space-time isn't just a special case of Newtonian. There are fundamentally different structures. So here, time is fixed and space is separate. When you get to special and general relativity, you can't split them up. And it's not just that splitting them up is a special case, like they're fundamentally intertwined. So it kind of stops there. I think it's now 28, so we have 2 more minutes. So I think that's probably all we have time for. Thank you.